So I'm doing a bunch of people on lunch, so I'll try to make this short and painless. I'm Jeff Underhill. I work for a group at AMD that focuses on HPC technology. And today I'm going to take a look at advances in multi-core technology, a high-level view of the roadmap, and then some acceleration strategies that we're working on as well to augment the progression of multi-core CPUs. So HPC's value is rising. A lot of people that we talk to are seeing more and more uses in a commercial. Sorry, let me just get this so I can see what I'm presenting. In commercial spaces, and as the capabilities grow, people can do more simulations. They can get more accurate results, and that offers significant ROI on the investment on these platforms. So to society, it's important, critical for medical advances, drug discovery, finding new ways to solve the energy problems that we're creating with all these high-end processors, and of course the vendors. It's one of the fastest growing segments, if not the fastest growing segment of the server space, according to IDC. And we're seeing a lot of commercial people taking advantage of HPC-like technologies as a competitive advantage to get their products to market quicker. So very brief history. AMD's been doing HPC for a little while, not as long as a lot of people in this room I know, but back in '99 at a AMD Microprocessor Forum, we announced the intent to introduce multi-core processors, multiple cores on a single die, and 64-bit support. In 2001, we entered the HPC market with what was then the Athlon MP. That was AMD's first multiprocessor offering. And then in 2002, started to cultivate the HPC ecosystem and tools and libraries and things like that in preparation for the launch of the Opteron in 2003, which at the time it was the first 64-bit x86 processor with a direct connect architecture offering scalability that hadn't been seen before within the x86 server space. So 2005 we saw the introduction of dual core, and then in 2006 we acquired ATI Technologies, which bring GPU and chipset capabilities to the AMD portfolio of IP. And then, of course, more recently, in fact, 2 months ago to the day, we launched the quad-core AMD Opteron, and codenamed Barcelona, and my marketing people slap me every time I say Barcelona these days, but it's kind of ingrained. And it's the world's first native quad-core x86 processor, and we're seeing some great performance results on that part, and I'll look at a couple of areas as to why that's the case here. So with the quad-core processor, we took a look at the architecture, and rather than just making 4 cores and fitting them on a CPU, we realized in order to capitalize on that performance, there's going to have to be some other changes. So there's really 4 key areas that we looked at. One was investment protection, maintaining a common core strategy. We released DP and MP products at the same time, and also a common socket strategy that allowed people to migrate their products they have today and minimize the impact on our technology partners who are developing platforms. Virtualization, it's kind of an interesting topic in the realm of HPC. When we talk to people, we get the whole gambit from virtualization doesn't matter to HPC. I want every cycle of my CPU doing useful work. Other people that believe it's an underpinning and enabler for grid-like technologies. And then other people that say, you know what, it's coming. We are going to get to virtualized environments at some point. So today I want to focus primarily on the performance enhancements and the power efficiency, because they're what I believe are more immediately applicable to this audience. So one of the key changes we made, we doubled the width of the floating point unit in this processor. So you've got double the number of cores as well as double the width of the floating point. But probably as important, if not more so, we widened all of the pipes in the CPU so that you can actually get to that horsepower and take advantage of it. Oops, wrong way. Okay, so just a quick benchmark chart here showing a uplift for spec FP rate and spec int rate. This is comparing a current generation dual core Opteron at 3 gigahertz with a 2 gigahertz quad core Opteron. You can see there for spec FP rate, we're getting a little under 50% uplift, and for spec int rate, up to 57% throughput improvement. So a lot of the reason for this is obviously that widening of all the pipes internal to the CPU, But as we'll see in a slide here or two, we've also re-architected the cache structures and added a lot of features to the memory controller to improve overall performance. So that's the 2 gigahertz as launched. Later on this year and going into next, we'll see frequency improvements as well that will raise that significantly. So we have dedicated L1 still in this product, and I'm assuming people are somewhat familiar with Opteron, so I'm just going to point out the changes that were made in the quad core. One of the main changes here is we allowed 2 loads per cycle on the L1 cache, so we've doubled the bandwidth. We've also allowed the core hardware prefetcher to fetch data directly into the L1 cache. Somebody a little earlier was saying that caches are not kind of helpful to HPC workloads. So this allows us to bypass code having to traverse those cache hierarchies, and it also saves us from polluting other layers of the cache unnecessarily. So we've maintained an independent L2 of 512K per core. So each CPU core does have a usable workspace dedicated to itself. New in this product is a shared L3 cache, and this serves a couple of purposes. Number one, we have a large amount of cache that the whole CPU can use, but it also allows us to do efficient communication between those cores on the die. So for snooping and things like that, and cache coherency, we don't have to exit the chip in order to do that. So this is a sharing-aware replacement policy that we've got in there, and it's sharing-aware, not shareware, I should add. So this will keep data more in the L3 if it realizes it's used by more than one of the CPU cores. So we still have an integrated memory controller. We've had that since the introduction in 2003. But we've seen the need, of course, to improve on the delivered bandwidth. A couple of people I've heard point this out already. Memory technology is not advancing anywhere near as quickly as the number of transistors we have and the number of flops that we can pack into these CPUs. So comparing with the current generation of dual-core products, we added a bunch of enhancements to the memory controller to improve the delivered bandwidth. So we can see up to 40% incremental bandwidth with the exact same memory technology by improving on the write bursting, the DRAM page turnarounds. A new feature in this memory controller is that we can fetch data into the memory controller itself and hold it in buffers in the memory controller. Somebody said the hardware prefetchers are intrusive with HPC codes. This is one way that we try to mitigate some of that, and if we inaccurately predicted the need for that data, it's only in the memory controller and we could throw it away. We haven't polluted our cache hierarchies. And then on top of that, the 128-bit wide memory bus on the Opteron chip used to be either it's 64-bit or it's 128-bit. Now you can use that as 2 independent 64-bit channels. So this improves bandwidth by up to another 10%, because if you're only fetching or using bytes out of that fetch, you have to fetch 128 bits to get that data. Now you can do 2 simultaneous fetches from the DRAM controllers. So if we look from a scalability standpoint, and this is an example looking at fluent speed-up performance. The yellow bars there are ideal scaling, so going from 2 to 4 to 8 cores, or 2, 4, 8 threads. And then the green bars show a 2 gigahertz quad-core Opteron. And you see there as you go from 2 to 4 cores, you get pretty nice scaling, not linear, but pretty good. But more importantly, as you go from 4 to 8, because of that balanced system approach, the increased memory bandwidth, the scalable I/O bandwidth, we're able to continue to scale. Now, if you want to buy quad-core CPUs and only run threads on 2 of the 4 cores, okay. If you want to use your quad-core processor and actually put it under load and get throughput, then that's where this complete balanced platform approach really begins to shine. And of course, the majority of x86 servers are used in a cluster environment, so scale-out performance is as important as scale-up performance, if you will, in the node. So this is a LS Dyna example, 1, 2, and 4 nodes, and again, you can see the green bars. We're getting some nice scalability out of this platform. So I've already touched on virtualization and its implications to HPC. Just wanted to point out to one change that we made here in the quad-core, and that was to add nested page tables to reduce or remove the burden from hypervisors and having to maintain shadow page tables and swapping things in and out. So we have a much more efficient virtualization implementation. So this is all wonderful, but of course, again, we've heard the limit going forward is going to be power. So while we were developing this chip, we took a look at ways we could improve power. And these are some of the innovations that we've included. One is the ability to dynamically control independently the frequency for each of the cores in the CPU. AMD Core technology allows the chip to disable portions of logic that it's not using and have it turned back on in time for it to use it. So the memory controller can turn off the read logic while it's doing writes and vice versa. Another key feature, we've split the power planes in this part so that we independently power the North Bridge and the CPU cores. This helps from a performance and a power standpoint, because from a performance standpoint, we can actually raise the voltage of the North Bridge and clock the North Bridge higher in some cases. And then the flip side of that is we can reduce the voltage on the CPU cores to conserve power, but keep the North Bridge at maximum frequency so we're not impacting the rest of the system. So HPC, kind of where it's going. You'll see in more use of HPC. The workloads are getting larger and more complex. People want more detailed results, and they want them quicker than ever. So CPU performance is on some trajectory, and it's going to continue on that trajectory. But the various uses we're seeing for HPC today, and the amount of data that people are using, we've got this kind of red curve going on, and people are at different points on that timeline. Some people, they've got enough performance today, but they see the problem on the horizon. Others are right on the cusp of that kind of intersection point, and others are like way into the yellow and red gradient there with, I've used all the power I can get and I need more, what am I going to do? So, where do we go from here? $1 million question. x86 improvements, we're going to continue to architect our chips and improve things there. IPC improvements, more cores, et cetera, delivered bandwidth. GPU and stream processing, as we've heard from NVIDIA, that's an area that AMD is also investing. And then dedicated accelerators like the ClearSpeed guys and others that augment the general purpose CPU platform. And together, everybody's talking about this as a heterogeneous computing, and hopefully that's not vaporware and smokeware there. It'll become real. So looking at the roadmap at a very, very high level, we're at the point here, the 65 nanometer quad core has just been introduced. As I mentioned, we'll exit the year and go into next year with frequency improvements. Next year, there will be a shrink of that product and some enhancements to the CPU cores to improve the IPC throughput. And we'll have options for larger caches and things like that. And then into 2009, we'll have a new platform with 4 Hypertransport 3 links, DDR3 memory, G3MX memory technology, which allows us to increase the capacity and bandwidth of the memory, IOMMU, and a completely new core, which I'm not at liberty to talk about, but I'm sure we have a bunch of meetings over the next week here. So then from an accelerated computing standpoint, we're seeing platform acceleration today through Hypertransport and directly attached accelerators, the GPGPUs. Going forward, we'll have options for tighter levels of integration of that at a chip level, package level, and ultimately at the silicon level if it becomes ubiquitous enough. So this is just one quick example of a market processing application. The blue chart there shows a software-only implementation, and you can see the spread of data there and the kind of latencies that were involved. The majority between 500 microseconds and kind of 1200 microseconds. And then the yellow chart is kind of the spike which they were able to achieve with an FPGA implementation by taking the core algorithms that they could accelerate and that are used more often, and you see it's much more deterministic down in the kind of 10 microsecond type time frame. So obviously this is difficult to achieve, but those are the types of things that can be done. This week, AMD just announced the first double precision capable GPGPU product, and this will be demonstrated at our booth at Supercomputing, and a new software development kit to go with that to try and make it easier for people to use and access the performance of these processors. So up to 500 gigaflops single precision performance, and 128 gigaflops of double precision performance. We'll have 2 gigabytes of onboard memory there. And obviously, it's a PCIe interface, so it's supported in a bunch of platforms already today. So not to trivialize the software implications, it's all very well to get up here and say we're going to have a gazillion cores and people are going to be using accelerators and GPGPUs and all this good stuff. But that causes a lot of software challenges for the ecosystem at large, and they're things that we all need to work on together in order to address. And I'm not going to go through these, but the key message is that AMD is aware of this. We're actively involved with the software community. Sun, as a key partner, obviously has tools, OSs, etc. So we'll be working with them to optimize for our multi-core processors and accelerators as time permits. So fundamentally, strong partnerships are obviously key. We feel we've got the best engine, obviously in the business, but until you wrap that in a chassis and put some wheels on it and do all the right things to make it into a platform solution, it really doesn't go very far. So obviously we're very pleased to work with Sun and have a world-class vendor like Sun who knows all about networking and system solutions, OS, CPU architectures, the whole thing. And by the way, this only works with a green engine. Blue engines are bad. Okay. And last but by no means least, I just want to acknowledge and thank both Sun and TAC for the work towards the Ranger platform, which is going to be one of the fastest supercomputers, if not the fastest supercomputer on the planet once it gets turned on. And Jay, I believe, is presenting tomorrow on more details. So with that, I'm going to say thank you. This is me on a bad hair day. And let you guys go to lunch unless we have time for questions. I don't know. Do we?
Yeah, we have a few minutes for questions, obviously.
Okay.
I was just wondering on the availability of the quad-core chips, what the lead time is.
Yeah, that's a great question. So clearly, we launched the parts back in September the 10th, and it's been 2 months now, and there's definitely been availability challenges, let's say. We've seen clearly unprecedented demand for it. There was a lot of pent-up demand, and we had a couple of high-profile opportunities where we had commitments that we needed to fulfill, so we did. And then we've had some tweaking to do on the processor design to match it more closely to the process technology. We don't have yield issues or process issues. It is more kind of tweaking the design to the process. So actually, by the middle of next week, there is going to be significant ramp of parts and increases in frequency available. So it's been challenging to this point, but it's only going to get easier here in the next couple of weeks. Actually, I'm not sure of the exact lead time right now. It depends via which channel and things, so that there's some more nuances to that than just hey, it's this long. So, but we can certainly dig into that and have that conversation. Yep.
Jeff, a question I have is that AMD has traditionally been in the volume business market for desktops and the like. The dedication to HPC is nice, but how much volume does this make up, or how much business is this for AMD, and how do we know that the emphasis will continue to be put on HPC versus the mainstream desktop?
Yep. So, again, a very good question. And I think you'd be surprised by the amount of business that AMD does now as a result of the server market, which encompasses HPC. Sure, traditionally desktop was the bulk of AMD's business. The reality is, over the past 2 or 3 years, the server business has actually been very good for AMD and has provided significant revenue. So it is a prime focus. I'm actually part of a team that was formed earlier this year, in January this year, to focus exclusively on HPC, which itself, I think, lends to an increased degree of dedication to that market. And then, of course, with the acceleration and stream and other things, the HPC market are going to be the first consumers of those types of technologies. So that is also very key to us. So I would expect a level to increasing commitment to HPC from AMD. And we're actually involved in helping define some of the future architectures of our CPUs as well, with HPC in mind and being representative of this community, which is one of the first times that AMD's really looked at the product portfolio and said, okay, we've got a bifurcation of workloads here now, and the HPC guys want this, and traditional server guys want this. So there's definitely more emphasis on that now.